Hi, my name is Charita. Today I'll be talking about solid state batteries, the engineering race beyond lithium ion. For more than 3 decades, lithium ion batteries have defined portable energy storage. They power smartphones, electrical vehicles, aerospace systems, industrial equipment, and increasingly electrical grids. But conventional lithium ion technology is approaching a difficult engineering frontier. The problem is not simply that we need batteries capable of storing more energy. We need batteries that can simultaneously provide higher energy density, faster charging, longer cycle life, and better safety, wider operating temperature ranges, and manufacturing at enormous industrial scale. And these requirements frequently conflict with one another. Increasing density, for example, can create additional safety and thermal management challenges. Increasing charging speed can accelerate degradation. Making a battery safer can sometimes require additional materials that increase its weight. One technology attempting to overcoming several of these compromises in a solid state battery, but the term solid state battery can be misleading. A solid state battery is not simply a conventional lithium ion battery in which somebody removes the liquid electrolyte and replaces it with a solid material. That apparently simple substitution changes almost every important physical process occurring inside the battery. Ion transport changes, interfacial chemistry changes, mechanical stress is becoming critical. The way lithium is deposited and removes changes, manufacturing processes change, and even the definition of the good electrolyte interface change. To understand why solid state batteries are simultaneously so promising and so difficult to commercialize, we need to go inside the cell. Why conventional lithium ion batteries have a limit? A conventional lithium ion battery contains four fundamental components: a positive electrolyte. Hi, my name is Charita. Today I'll be talking about solid state batteries, the engineering race beyond lithium ion. For more than 3 decades, lithium ion batteries have defined portable energy storage. They power smartphones, electric vehicles, aerospace systems, industrial equipments, and increasingly electrical grids. But conventional lithium ion technology is approaching a difficult engineering frontier. The problem is not simply that we need batteries capable of storing more energy. We need batteries that can simultaneously provide higher energy density, faster charging, longer life cycle life, better safety, wider operating temperature ranges, and manufacturing at enormous industrial scale. And these requirements frequently conflict with one another. Increasing energy density, for example, can create additional safety and thermal management challenges. Increasing charging speed can accelerate degradation. Making a battery safer can sometimes require additional materials that increase its weight. One technology attempting to overcome several of these compromises in solid state battery, but the term solid state battery can be misleading. A solid state battery is not simply a conventional lithium ion battery in which somebody removes the liquid electrolyte and replaces it with the solid material. That apparently simple substitution changes almost every important physical process occurring inside the battery. Ion transport changes, interfacial chemistry changes, mechanical stresses become critical. The way lithium is deposited and removed changes, manufacturing processes change, and even the definition of the good electrode electrolyte interface changes. To understand why solid state batteries are simultaneously so promising and so difficult to commercialize, we need to go inside the cell. Why conventional lithium ion batteries have a limit? A conventional lithium ion cell contains four fundamental components: a positive electrode, commonly called a cathode, a negative electrode, commonly called anode, a porous separator, and an ionically conductive electrolyte. During charging, lithium ions leave the positive electrode and move through the electrolyte and separator towards the negative electrode. At the same time, electrons cannot travel through the electrolyte. They therefore travel through the external electrical circuit. During discharge, this process reverses. Most conventional lithium ion batteries use liquid electrolytes consisting of lithium salts dissolved in organic solvents. One commonly used lithium salt is called lithium hexafluorophosphate. The electrolyte has to perform a surprisingly difficult balancing act. It must allow lithium ions to move rapidly through the battery while preventing electrons from traveling internally between the electrodes. In other words, it should be excellent ionic conductor, but a very poor electronic conductor. The liquid also needs to penetrate the microscopic pores of the electrodes, remain chemically stable for long periods, and function across through the charging and discharging cycles. But conventional organic electrolytes have another important characteristic. They can be flammable. This creates one of the central engineering challenges of the high energy lithium ion cells. As battery energy density increases, increasingly large amounts of electrical and chemical energy are concentrated inside a relatively small volume. Mechanical damage, manufacturing defects, internal short circuits, extreme temperatures, or severe overcharging can initiate unwanted chemical reactions. Those reactions generate heat. Higher temperature can accelerate additional chemical reactions. Those reactions can still produce more heat. Under sufficiently severe conditions, this feedback mechanism can produce what is known as thermal runaway. Thermal runaway is a condition in which heat generation inside the battery becomes self accelerating and extremely difficult to stop. Solid electrolytes are attractive partly because they can substantially reduce the amount of volatile and flammable liquid inside the cell. But improved safety is only part of the solid state battery story. The potentially transformative advantage involves the negative electrode, the lithium metal opportunity. Most conventional lithium ion batteries do not use pure metallic lithium as their negative electrodes. Instead, they commonly use graphite. During charging, lithium ions move into spaces between atomic layers of graphite. This process is called intercalation. Graphite has theoretical specific capacity of approximately 372 milliampere hours per gram. Specific capacity tells us approximately how much electrical charge can be stored for a given mass of electrode. Metallic lithium, in comparison, has a theoretical specific capacity of approximately 3,860 milliamp hours per gram. That is more than 10 times theoretical gravimetric capacity of graphite. Metallic lithium also possesses an extremely low electrochemical potential. Together, these characteristics make lithium metal extraordinarily attractive as a negative electrode material for high energy batteries. If lithium can replace graphite, it becomes possible to reduce the amount of comparatively low capacity material required on the energy side of the battery. And this is where solid state batteries become particularly interesting. The ultimate objective is not merely replace the liquid with the solid. The more ambitious architecture combines a high energy positive electrode, a very thin solid electrolyte, and lithium metal negative electrode. Some proposed architectures go even further. They attempt to remove the manufactured negative electrode almost completely. These are called anode-free batteries. We will return to these later because they represent one of the technically demanding forms of solid-state batteries. What exactly is a solid electrolyte? A solid electrolyte has to accomplish something deceptively difficult. It needs to behave like an ionic highway while remaining an electronic barrier. Lithium ions must move through it rapidly. Electrons should essentially be blocked. In a liquid electrolyte, lithium ions move through a liquid environment and while interacting with surrounding solvent molecules. Inside a crystalline solid, there is no liquid solvent carrying these ions. Instead, lithium ions migrate through positions available within the atomic crystal structure. Think of the crystal as a three-dimensional network containing possible positions of lithium ions. For an ion to travel through the material, it has to move from one available position to another. Some movements occur through vacancies. A vacancy is simply an unoccupied atomic position that an ion can move into. Other materials allow lithium movements through interstitial sites or through more complicated cooperative migration mechanisms, in which several ions move in a coordinated way. Every movement requires a lithium ion to overcome an energy barrier. This barrier is known as the activation energy for the migration ion. Lower activation energy generally means lithium ions can move more easily through the solid. Temperature also matters. As temperature increases, ions generally gain greater ability to overcome these migration barriers. This is why ionic conductivity is strongly temperature dependent. For practical barriers, researchers want room temperature, ionic conductivity, approaching that the conventional liquid electrolytes. Several modern solid electrolyte families have reached conductivity levels in the millisiemens per centimeter range, and some sulfide electrolytes can also can reach approximately 10 millisiemens per centimeter or even under favorable conditions. But extremely high ionic conductivity does not automatically produce a good battery. The electrolyte must simultaneously possess high ionic conductivity, extremely low electronic conductivity, chemical compatibility with lithium metal, compatibility with high voltage, positive electrodes, mechanical stability, low resistance at interfaces, thermal stability, environment stability, and the ability to be manufactured cheaply at the industrial scale. No single known material perfectly satisfied all these requirements. This is why several different families of solid electrolytes are competing with one another. Sulfide solid electrolytes. One major category, sulfide solid electrolyte. These materials can contain sulfur as a major component of their chemical structure. An important example belongs to the crystal family called argeterites. One widely researched argeterite electrolyte is based on lithium, phosphorus, sulfur, and chlorine. Another important group consists of lithium, germanium, phosphorus, sulfur based materials. The major attraction of sulfides is extremely high ionic conductivity. Sulfur atoms are relatively large and highly polarizable. In simplified terms, this can create comparatively soft crystal environment through which lithium ions can migrate efficiently. Some sulfide electrolytes can therefore achieve ionic conductivity approaching that of conventional liquid electrolytes. Sulfide have another useful property. Many of them are mechanically softer than rigid oxide ceramics. Why does softness matter? Because the surfaces inside the battery are not perfectly flat. Electrolytes consist of microscopic particles. Those particles expand and contract. Surfaces contain irregularities. Tiny gaps can appear. A soft solid electrolyte can deform under pressure and maintain physical contact with electrode particles more effectively than the extremely rigid ceramic. But sulfides introduce serious complications. Many sulfide electrolytes are extremely sensitive to moisture. Composure, exposure to atmospheric water can trigger chemical decomposition and in some cases generate toxic hydrogen sulfide gas. This means electrical manufacturing require exceptionally dry and careful controlled environments. Oxide solid electrolytes. Another major category consists of oxide ceramic electrolytes. One of the best known as examples is the lithium, lanthanum, zirconium oxide. Researchers frequently refer to this material letters as LLZO. It belongs to a family of crystal structures known as garnets. Lithium, lanthanum, zirconium oxide can provide good lithium ion conductivity, strong thermal stability, potentially useful compatibility with lithium metal. But ceramic electrolytes introduce a major mechanical challenge. They are rigid. Imagine pressing two perfectly smooth pieces of glass together. They may appear to touch over their entire surface. At microscopic level, however, the true contact area can be much smaller because if every real surface contains roughness and imperfections. The same problem occurs inside the solid state battery. A liquid naturally flows into the microscopic irregularities, a rigid ceramic cannot. Tiny gaps therefore increase electrical and electrochemical resistance at the surface level. Even worse, current may become concentrated around the limited areas that remain in contact. The interface is the real battery. This brings us to perhaps the most important idea in solid state battery engineering. Interfaces can dominate the performance of entire battery. Consider a positive electrode particle. In a conventional liquid electrolyte battery, liquid can penetrate through a porous electrode structure. It naturally wets much of the available particle surface. A solid cannot flow through an electrolyte in the same way. Therefore, the positive electrolyte electrode of the solid state battery usually needs to be carefully engineered composite. That composite can contain active positive electrodes, particles, solid electrolyte batteries, electronically conductive materials, binders, and some protective coatings. Now, several things must happen simultaneously. Lithium ions need a continuous pathway through electrode. Electrons need a different continuous pathway, and those two pathways must repeatedly meet at the surface of the electrochemical active particles. This creates what engineers call a percolation problem. Percolation simply means creating a continuous network through a material. Imagine pouring thousands of conductive and non-conductive particles into a container. If there are few conductive particles, they remain isolated. Once enough particles connect to one another, a connective pathway forms across the material. A solid state composite electrode requires a type of connectivity in both ions and electrons. Poor distribution is either requires network reduces much of the active material can actually participate in the battery reaction. Thank you.